everybody, and welcome to CS202 video 15. Hope you all are doing fine this fine evening. So today we are going to continue talking about linked lists. We are going to be building a linked list. We're going to be coding a doubly linked list. So let's go ahead and start by figuring out what a doubly linked list is. Okay, so oh no, I don't have water. Okay, stand by. I'm going to go ahead and get some water, and I shall be right back. Okay, all right, I went ahead and got some water, and now I'm back. Okay. Hello. So, yeah, especially linked lists, we're gonna need a lot of water. Okay, so, by the way, I was thinking about something. When you guys watch the operator overloading, in that video, do I go over the copy constructor and the rule of 3? Do you guys remember? If I went over that. Otherwise, I shall incorporate it into maybe tomorrow's class. Not the copy constructor. Okay, so in that case, maybe I will go ahead and I could talk about it today, but more than likely I will talk about it tomorrow, just because it's useful. So yes, okay. So if you're curious, you can Google rule of 3 programming, C++ programming, and I'll post a link here in case. So that is from Wikipedia, and it's a combination of the destructor, the copy constructor, and the copy assignment operator. And it means that when you overload one of those, you gotta overload the other 3. They always come in 3s. If you only do one of them, you risk doing something bad in your program. Basically, the quickest example of that is if you got something with dynamic allocation that requires you to create a destructor so that you can deallocate something in a class. If you go ahead and assign that variable object into another object, that dynamic allocation, you know, when you assign it, it's going to be a shadow copy. It's going to cause problems. Because of that, you got to overload the copy assignment operator. And then the copy constructor kind of goes along those lines because it kind of works like assignment. So we can go over that in detail if you have time tomorrow. If not, then you should definitely check it out, as it's a good thing to know when programming. So yes. The app that we're working on is not out yet on iPhone. Hopefully it's out today or tomorrow. But stay in touch, because we might be running some sort of test tomorrow on Discord. So I'll let you guys know. We're trying to get the app out on the iPhone yet. It's out on Android, but it's not on iPhone yet. So hopefully tonight. We'll see. We're waiting on Apple to respond on a couple of things. So yes. Okay. So anyways, I'm glad that I remember that, because then I put it here. So maybe we'll talk about that tomorrow with the copy constructor as well. But okay. So with the linked list, we We said that typically it's made up of nodes, and these nodes have two components in them. And that is basically the data component and some sort of pointer that is a link component, also used next, right? That's what we were using. And so that link, it basically hooks it to another one of these nodes, and you basically make a chain of them or a list of them, and that is your link list, right? Okay, so before I define what things you would want to have in a linked list, let me define a different kind of linked list. Or it's not different, but sort of enhanced version of a linked list. One nice little feature that you could have in a linked list is the ability to go forwards and backwards. While this is not going to resolve the initial disadvantage of a linked list, which is that you can't easily access things in the middle, it is going to cut down the potential access time in half to get somewhere into the middle of the list. But it's not going to magically make things better. It's still useful. And so because it's still useful, it might be worth exploring. And that is what is known as a doubly linked list. Okay? The ability to go forwards and backwards. Because this is a singly linked list. And the name implies that it's singly linked. So there's only one link between each of the nodes. Doubly linked list is going to be a double link. And what that's going to look like is our nodes, instead of just being made up of a data pointer and a link pointer, they're going to be made up of a data pointer and two link pointers. There's going to be one in the beginning, per se. I mean, of course, when you're declaring this as a struct or whatever, it's not really, it doesn't matter the order of the variables, but at least to better visualize it, I want you to think of it this way. In the center, we still have the data component. On the right-hand side, so that way, we are going to still have our link component to go to the next node in a sort of a forward direction. However, the new thing is on this side here, we are going to be creating another link component called previous or prev. And so now using this basic template of a node that has two pointers, we can go ahead and connect a bunch of these on either direction. So for example, we can go ahead and link them together like that. And then what does this actually mean? Well, it means a couple of things. One of them, it means that we are going to have two null pointers in the list at any given time. That's going to be up here, the previous pointer that is the first item or node of a linked list, that previous pointer is going to be always null because it's pointing to nothing. And then of course the last item of the list is going to be pointing to null. The in-between nodes are going to have basically two links they can go to, the next node and the previous node. And so if we draw this as for like a lot of lists, for a lot of nodes, let me go ahead and do that. Maybe I'll make it smaller so we can fit a couple. What that would basically look like, oh, there we go. Something like that, okay? Although, hold on, those arrows look different. Let me use the same arrows. There we go. So that would be essentially what the linked list would be looking like. Maybe let's put one more node, and then let's go ahead and set these to null, and that to null. Okay, and so this adds a little bit of complexity when you're inserting and deleting your nodes, because you have to change two pointers instead of one, potentially. However, you're able to go in both directions of the linked list. So if you want to print it backwards, you can, just by following the pointers. The only other way that you could print a linked list backwards is with recursion, actually. If you had a singly linked list and I asked you to print that list backwards, you can't do it iteratively unless you use some sort of stack. To like hold off the information before printing it. The easy way to do it was just recursion. With a double linked list though, you can follow the pointers backwards and do that printing iteratively. In addition to this, you typically have a head pointer, which is pointing to the first node or pointing to null in the case that there's nothing in the linked list. Now you're also going to have a second pointer called tail, which is going to usually be pointing to the last item of the linked list, or in the special case that there's only one node in the linked list, then it's going to be pointing to the same location as head, or if there is no items in the linked list, then it's going to be null. Other than that, everything is still the same. So why really use this? Again, you can go backwards. That's an advantage. You're still limited when you're trying to insert or delete something. You gotta search the list potentially, which does mean moving back and forth. It's a nice sort of lead up to in 302 when we're talking about binary trees. Okay. So that's one of the also usages of it. So it's a good thing to practice, especially because now you got to handle two pointers left and right when you are trying to delete something. So for example, let's go ahead and say that we want to delete, in this example, one of the nodes. Let's say that the hardest case is, of course, if it's something in the middle. So let's say that we want to delete this node right here. Okay, what we need to do is we need to actually change two pointers of other nodes. We need to change this pointer and we need to change this pointer. We need to make this point here and we need to make this point here, and in the meantime have some sort of temporary pointer that points here, so that once we go ahead and set the pointers, then we can go ahead and call delete on that. So step 1 is going to be this one, step 2 that one, although either way, and then step 3, actually I suppose step 0 would be to set that pointer, 1, 2, and then step 3 would be to delete temp. Okay, and so this is what we're going to be coding as well. So yeah, that's pretty much it. Let's talk about the two kinds of linked lists that you usually have. I believe I said it last time, but let's just write them down. We can have an unordered, and ordered linked list. An unordered linked list is you just throw things in any order you want. Basically just whatever. It's like you make an array and you just throw things into the array. The ordered linked list is a special kind of linked list where the items are sorted. Okay? Now, what does it mean to sort something is a little bit into like 302 land, but for now, let's just think of the most basic sense of things being in ascending order, or what is also known as non-descending order, right? So like, if you got numbers into the linked list, then it's going to be like 1, 2, 3, 4, 5. It's not going to be like 1, 5, 2, 3, 8, 0, -5, 20. No, it's going to be a specific order, okay? And we're going to be doing that version, I think, because it's a little bit more interesting. Because what that means is that when you're inserting something into your linked list, you're going to run into a situation where you actually have to figure out where it goes. And when you're doing that, so when you're inserting, there's a couple of scenarios that you got to consider. That the list is empty, in which case that's easy because you just insert at the beginning. You got another scenario where the list has, or the item you're inserting at the beginning of the list. So insert at start of a non-empty list. So anything down here is a non-empty list, but it's the smallest number you're inserting. So in this case, you would be inserting it at the start. Then other scenario could be item is insert or insert item at the end, which in the case of a sorted linked list is probably because it's the biggest number. So in the first one it will be because it's the smallest number you're inserting, and the other one is because it's the biggest one. So in that case, you have to traverse the linked list all the way to end to insert it, or if you got a tail pointer, you can just insert it right there. And then finally, the hardest one I'd say is item insert in middle. Which by middle, I am saying that there's at least one node that is greater than what we're inserting, and at least one node smaller than what we're inserting. This one is the one that's trickiest because we actually have to kind of find the location first, and then go ahead and move those 2 pointers around, right? So in the case of this one here, if we're trying to insert something into the doubly linked list, let's go ahead and kind of pre-visualize that. So suppose that we want to insert, first of all, create your new node that you're inserting. So, we got the node right here. In fact, actually, maybe I can just take this one. Okay, there we go. And then let me just set it all to null. And so let's say that as we're looking at this, this is let's say this is like 1, 3, 6, 8, and 9, and we're trying to insert a 5. That's pretty much in the middle. Okay, that's gonna go right there. So what we need to do is we need to first traverse the linked list and get here. And once we're here, let's say that we're holding a pointer called cur that is pointing to this node. Okay? Once we're doing that, what we need to do is we need to be very, very careful and first copy cur next into, and this is called, our new node has to have a name when we allocate it. So let's just call that one temp. Okay? So what we need to do is we need to copy cur next, which currently has this pointer here pointing to from 3 to 6. We need to copy that value into temp next. Doing that is going to basically make this point to 6. Okay, good. The next thing we need to do is we need to make 6 point back to 5. So we need to make that point back over here. To achieve that, what we can do is we can access that pointer by saying cur next, which is going to take us to the next, because remember cur is 3, so cur next would be this one here, cur next is this here, and then cur next would be this next over here, which is exactly what we want. And so that is what we need to modify. Or sorry, no, not next. My bad. Previous. Because we're trying to update. Actually, this was misleading how I put the arrow there. I got confused. This is what we need to update. This one, okay? So we need to update cur next previous to point back to the 5. Okay? So in that case, we can make that point to temp like that. Okay? And so, yeah, because we're trying to link it back. Okay, we don't need to mess with cur next because that's pointing to the 8. That's okay. Okay, so we got halfway there. We need to do 2 more. We need to update temp previous. That needs to point back to 3, which is currently held in cur, which is that makes it easy because you just do cur. And then so that what that is doing is basically changing this to point to this. And finally, well here, so it's easier. I'm gonna put it like that. Finally, we need to change this guy to point there. And now that's the last pointer that we change, because if we change this in a different order, especially for this pointer, we might lose access to the other things before we can link things together. Okay, so that's the last one you want to do. So now that one's going to be cur next is equal to temp. Okay, so as you can see, it's important that you're doing this in this order, because otherwise you can't do this line. If you change cur next before you do this line, then you're essentially going to break this algorithm and it will not work. Okay, so yes. So that's the trickiness about inserting, and then deleting will be something similar. So that we'll code it. So okay, so that's the difference between ordered and unordered. It depends on how you're inserting things. So the last thing before we start coding, I want to summarize is what are the different features or functionalities that a linked list should have. And these are the same ones that per se would have something with any data structure that you're storing information. And so you need to be able to insert into the data structure. So you want to insert information. And in the case of the ordered linked list, depends on how you insert, the way we said. In the case, if you're inserting in a specific way, or if you're just inserting at the beginning or inserting at the end, you could have, that could be a couple of functions there. Or if it's just called insert because it's trying to insert in a specific order, that's another way of doing it. Okay, but you have some sort of insert of some form. On the other hand, we also want to have something to delete, right? So by delete, I'm not necessarily just talking about deallocating. I'm talking about being able to remove things from the list. And in that case, typically, while yes, you can say delete beginning, delete end, or something, or delete this specific index, we could also have something where we search for a specific item to delete as well. So some form of delete is very important to have. The other thing that it could be relatively useful is some sort of print to be able to see what is in the list now. And those are pretty much going to be the most basic things, because I mean, like, we need some sort of support functions. Like, we need a way to create a node that's part of insert, probably. We of course need ways of deallocating stuff, which again is probably part of delete. And there could be a sort function, inside of these, so it can sort the linked list for us. But again, that's 302 land. And I think that's pretty much it. Now, how we will achieve this is we're going to need a class, and we're going to basically make a class called linked list or double linked list, like that. And we're going to basically just all the stuff we're going to throw in there, right? And so to be able to do this, we are going to need some specific situations here for the linked list, which are to have a head and a tail node pointer, right? And our constructor is going to be relatively simple because it's just going to set these things to null. The destructor, however, that's going to be tricky because we want to make sure that the destructor deallocates the linked list before it go, when the object goes out of scope. So that is going to be rather interesting. And technically speaking, because we are going to do something to the destructor, we do need to talk about, again, to handle the rule of 3 thing. So like, even though we're not going to try to take a linked list and assign it to another linked list, if we were to do that, we would have to overload a copy assignment operator. And then if we try to make an object out of another object using the copy constructor, we'd also have to overload that because of the same reason. Otherwise, we're just making shallow copies to this thing. So, but again, if we have time, I'll talk about that copy constructor stuff. If not, don't worry too much about it, but still learn it on your own time because it's a useful thing to know. Okay, so that concludes sort of the prep, and so now we can actually go ahead and start programming. Does anybody have any questions before we start coding this thing? Okay, that was interesting. Here we go. Let me know if you have questions. Yes, OBS recursion indeed. Let's see. This is the Fibonacci stuff. So doubly linked list.cpp. Let's make it up lowercase. Okay, we are now ready to go. So no questions, I guess. Okay, so let us begin. The first thing that we are going to code, and again, I'm not really looking unless we get stuck. More than likely we will get stuck and probably crash at some point. That's okay. It's part of the learning experience. But technically speaking, what we're going to do, I've already coded or at least done something very similar in the class sample codes that are posted online on Canvas page. So yes, those are there. So we could definitely pull those to reference if we get stuck, but I think we pretty much can do this from memory for the most part. So the code will look similar, but it may not be the same as whatever we have there, okay? So the first thing that we're going to do is we are going to create a class for the nodes. Now this class has to be public to make life easy. So we're gonna use, you just call it node or node type. What do we want to do? I think we'll go with node. And so this class, again, like I said, it has to be public so that things are easier. By the way, I never actually said this explicitly, but never make your constructor or destructor private. That's just a terrible, bad idea. It will compile until you actually try to make an object of that class, and then it will not compile. So yes, I guess back to first week class when we talk about object-oriented programming and you're talking about classes and things like that, always make your constructors public, unless you know better, okay? Which probably, unless you have a lot of practice with it, you probably not. So just stick with making them public. Now, other things, yes, getters and setters, but the constructor should be public because otherwise the thing will break. Like, you know, I can show you really fast. Like, this should compile. Well, if I put the curly bracket, it will compile. However, the moment that I try to make a class, I get an error saying that node parentheses is private within this context because the constructor is private. So I can't even make a class at that point. So that's bad. Okay. So there are some ways that there might be a purpose of this. If this class is like internal as part of inheritance or something like that, then you could make it like protected. But no. Okay. So yeah. Anyways. All right, so our node class is a doubly linked list. So we're gonna want it to have a previous and a next pointer. So we can do that by saying previous and next like that. And then we also wanted to have data. Do we want to be hardcore and make it templated? Yeah, let's try it. We might regret this later, but we would definitely try it. So we're making a class T data, okay? And so that is going to be our basic node. However, I do want to make my life easy by adding a constructor and forcing that constructor to require a value so that you cannot just create an empty node with like invalid data. You have to give it the valid data at the moment of creation, okay? And so because of that, I am going to have a parameter here. So let's call it D. And then data gets populated with D, and then previous gets a null, and next gets a null. That way things are done ahead of time. Actually, we don't usually use null PTR, so why don't we use null PTR this time around? Okay. That does mean I'm going to have to compile with C++11, but we don't really use null PTR often, so let's go ahead and use it today. then I guess go ahead and put the body of that like that. We don't really need anything inside of that. We could make this dynamic. We could make data to be dynamic. I'm trying to think of a purpose to make it dynamic that would be useful to us, but I can't think of anything. I guess that would make it more flexible. So yeah, let's make it dynamic. Why not? We're making this a little bit extra complicated, but I think it would be cool to have to do that. After all, I have to keep myself in containment and just go to the same thing every semester. So yeah, okay, so stash equals plus 11. So we're gonna make it dynamic, and because of that, then in a constructor we need to say data new t. New t. Is that going to be okay? Or are we gonna? Is it gonna ask me for a type? Oh, we'll see. Can't remember. Oh, didn't ask for a type. Well, okay, must be okay. Next, we want to add a destructor to this to the node, and that destructor is just the only thing it really needs to do is it needs to go ahead and delete data, and potentially, I suppose, not necessary, but you know, why not? Set these guys to null as well. It's getting deleted, but you know, why not? Okay, so there we go. Let's just very quickly test to make sure that our nodes work fine. So let's go ahead and dynamically allocate a node, and then access the node and try to store something in it. So let's go ahead and just make a test node by saying node test node gets new node, and here I think here is where we have to put that. Okay, and then let's make it an integer. I think that's the order things go. And then let's go ahead and put in a 42. Okay. Is data currently set to have its address reset to the value of D? Ooh, yeah, this could be actually an issue. Should try to assign this. We want to dynamically allocate it first and then set it to D. So yes, the address right now will be set. So you are correct in the sense that it was currently set, because because when I wrote this line of code, I was thinking it was going to be a static object, but then we made it dynamic. So yes, that would cause it to have data be stored to the address, and to take the value that's in D and store it as an address. So you're very correct in that sense, which is not what we want. So that's why now I went ahead and modified it. So yes, good catch on that, by the way. Hopefully we would have caught it when we try to compile this and it would have crashed. But yeah, okay, so we got a lot of scary errors here. So let's see, missing template argument before star. Okay. So node pointer here needs to have also an int here. And then has incomplete type. So these as well need to have node t. Why doesn't it like me putting a comma there? Strange, but what if I do this? Okay, interesting. I don't question why that fixed that, but I will just embrace that it's fixed and move on. Okay, so all right, let's go ahead and see if this worked. So let's try to just print it out, I guess. So cout. Let's make the node point to itself for some reason, just to make sure that it's okay. So test node next is going to be pointing to test node. Of course, it's bad, but again, we're just testing it. And prev is going to be pointing also to test node. And then let's go ahead and cout test node data. But that data is a pointer, so we need to dereference it. So we do that. And then if this works fine, then we should just get a 42 printed out. Okay, there we go. So it is working fine. Perfect. So we are good to go. In fact, let's just save that in a function called node tester. And then we can just throw all of that there. And then we can get rid of it. And we could just call it node tester. Heck, we could even make the node tester a templated function. You guys want to do that? Oh, I need a prototype. There we go. We could make that templated so that we could pass a parameter here and that parameter gets filled here. But yeah, why not? Let's do it. Just to not make it. No, that's just to not make it confusing. We'll not use T there. We'll say V instead of T. And so we can say template class V. And then that populates that. So then here, do that. And then the parameter here is going to be, we'll say it's just call it lowercase v. Like that. And then I do think that I think we're gonna need to put the word template in front of that prototype, but let's see if it compiles without. So yeah, okay, cool. So yeah, well actually we need definitely to put it because of the parameter. Otherwise this just gets confused. So template class. Cool. Now can I make this into one line? I think I should be able to. And it works for 42. But now we can test it with not just an integer, but we can call this function twice. And maybe the second time we can test it on a string. It's meta to fill a string with the word string in it. So, yep, it works. So our nodes have been successfully tested, okay? The idea of testing code with functions, by the way, is not something new. Actually, there's a whole subtopic of programming for that, which is called unit testing. You can go ahead and look that up on your own time. But yeah, that's going to be basically, you know, prove that our node works decently enough. Okay, so now we're ready to move on to. And by the way, I hope that today, I mean, this code is going to get pretty long, so you guys gotta be on top of it if I if something goes off the page and I'm coding and you can't see it. Does it need to be node prep next? Oh yeah, that may be why. You're right. That might be why this was not like that. Yeah. Well, well, let's test it. Only one way to find out. Yeah, there you go. And then just make sure that was working still by commenting this. Oh yeah, there you go. Good job on that. So yep, that's probably what I was compiling it for. Interesting that it's associated like that. It's only associating that to the next variable. So because I always think of that as being part of this part of the code. Like if the compiler I think would be like associating the asterisk to this part, but apparently it's associating it to the variable. So interesting that it's actually happening. That has like internal implications that somebody like Ben in 326 should hopefully explain as to why they decided to do that. but interesting. Cool. All right, so let's go ahead and make the linked list class now. So we're just gonna call it DLL, double linked list class. Okay. I guess we could write it out. I don't think that we need to refer to it too many times, so that name will be okay, even though it's long. And the first thing that we want to have in this class is going to be the word public. We may do some things privately here, like the head and tail. That actually, I think there is a certain value in making those private. So let's go ahead and make our heads and tails. So those are just node pointers. This is going to be a templated class because we have to deal with the fact that the nodes are templated. So yeah, that's just the fact of life. So then we were basically going to do the same thing that we did before with head and tail, which now we've learned that we have to do this way. So good thing on that. What else would be private? I don't think anything else. There's really the only data that you're really storing in this class is just that head and tail pointer. Everything else is our individual nodes that you're linking. So that's pretty much it. Yeah, and then you want your public functions to be able to access things. So yeah, really, I think that should be it. I mean, we can of course edit it as necessary. So yeah, okay. So let's go ahead and create our constructor to deal with these two pointers, because I don't want them to be not null when the list is empty. So if we get a double linked list, we're going to just make an empty one first. And so let's go ahead and just do that. So if we get a double linked list, we are setting head to tail to null. And again, I'm going to use null PTR for everything here, so make sure I don't use null. Okay, cool. So while we're at it, we could do the destructor, but again, the destructor is going to involve potentially deleting the entire list. So I'm just gonna write it here, but I'm just gonna say like, to do, so I don't forget. Okay. There's no real deletion required for the class. However, I'm gonna take advantage of that destructor to basically delete the linked list up here. Okay. So I'll just put it there for now. And now let's go ahead and write in our functions. So we need to have an insert and delete. And because this is going to be an order linked list, it doesn't really matter. We don't need to have like an insert at start, insert at middle, insert at end function. We just have a generic insert function, and that'll deal with the logic of finding where in the linked list this item will be. So to be inserted or to delete it. So we are gonna call it void insert, and then it's gonna have a parameter of whatever the data value is. So what's a good name for that? Yeah, data, why not? T data. And then we're gonna make that outside because it's gonna be a pretty big function, so yeah. And then also delete. That's probably a bad idea to call a function. Let's just call delete. Maybe we'll make it uppercase. Yeah, because like delete is a reserved keyword. So I think if we make it uppercase, it's okay. And then, oh, that delete, or del. Yeah, del. How about that? Yeah, that's a good one, del. I'm gonna go with del because it's less letters, so it's less typing. And then delete also will have a value passed in, which is what you're looking for to delete. So sort of a search and delete in one. In fact, that would be probably a good name, search and delete. But yeah, so we'll do that. Okay, and a good function to have as well is going to be print, which I just remembered as I was thinking about that. That would be something nice to have in our node class, is a print function. And that print function just basically prints out the node. So that could be useful to have. So cout data. And this This is not printing out the addresses of the pointers, but we could if we want. But really, we just actually not even an inline, just cout data. Okay. Technically, we don't need to have that function because data is public, but it'd be nice to just have. So I'll just leave it in there. It might come in useful later. Okay. Void print. Let's see. Just make sure that now let's throw it into our tester just to see, because now we can just go ahead and say test node print, and that will do the same thing as this line of code. And this is more of an object-oriented programming mentality to do that. Anyways. Parentheses. So 4242 string, perfect. So it's working fine. Should I do the end line in here? I don't know. Yeah, why not? We can no, because that's gonna be a headache. Because when I print out all the nodes, calling print is nice, but if I do end line, it's gonna print them only each their own line, which I might not want. So that's fine like that actually. So if I really wanted to have an end line, I would do it as its own thing here. So like cout end line. Okay. So yeah. Okay. So perfect. Just wanted to still make sure that that was working fine. All right. So yeah, I think that's all we really need: delete, insert, and print. I mean, we can always write more functions later. So let's go ahead and start out with the, well, print is the easiest one, but it's kind of useless to write that because we can't test it if we don't have things inside of the thing. So we're going to start out with the insert, I guess. Okay. So let's go ahead and write this little header thing, class T. And then in void doubly linked list T insert T data. I think that's the way you do that. Let me just check. Invalid decorator for the keyword insert. Oh, colon. Hey, there we go. Cool. All right. So that is how you do that. In fact, even though we're not going to write the body of those functions, let's just kind of put them in here for the other two. So delete, basically the same thing. And then print will be the same thing. Except that one doesn't have a parameter. Because it doesn't have a parameter, do we need? Yeah, we need to, because of this, we need to have it to make it templated. I think we do. Can we get away with it not being templated? I don't think we can, but here, let's test it. Yeah, so it complains. Okay, so yeah, all right, cool. So we do need to have that. Perfect. Even if we don't have a parameter and that's templated, it requires it because inside of it is going to be templated. So, yep. Okay. So again, these are to be done. You know, to do and to do, and this is where we're going to start coding right now. So far our code is about 60 lines of code, really, about approximately, because I mean we have the test function, so about 60 lines of code. So yeah, that's not bad. We're really I'm proud of this. This is very nice and clean so far. I mean, now it's gonna get crappy probably when we do the insert, but okay. So let's remember. Let's go ahead and actually pop the iPad here on the side. Let's make sure we remember the 4 scenarios that we have to deal with. Okay, we have, I said 4. Yeah, because we also have this one. The list is empty, so yeah. we have those 4 scenarios that we have to deal with. So that's what we're going to code, okay? So let's start with the easiest one. Because remember, divide and conquer, testing on each step. Don't try to code this whole insert function at once and then test it. It's a pain to debug in that case, Go with one of these 4 items, do that, test that specific scenario, and then go ahead and move on, okay? So let's go ahead and start out with the easiest one, which is that the list is empty, okay? The other ones that you're gonna write, and it might be a good idea to do this, at least I find this useful, is before you code it, write comments on what it is that you're going to eventually code. So, we gotta code that the list is empty, so insert on list empty, insert item, insert at start, insert at the end, and then insert at middle. Okay? So, however, before we can even do that, we need to search through the list to see where we insert. Okay? So, how about we do this one, because it doesn't matter. If the list is empty, there's nothing to search through. So this is some logic that just came up to me right now, because I wrote these comments down first to kind of critically analyze what it is that we're going to be coding, to make sure that we don't do something bad or dumb early on. We leave the dumb stuff for the end, once the code is complicated enough that we start making mistakes. So yeah, depending on where we find, is going to be those 3 kind of possibilities to insert. So let's go ahead and how can we easily detect whether or not the list is empty? And assuming that we properly are maintaining our null pointers, which we are, then an easy way to test it if it's empty is if head and tail are both null, or at least if head is null. Tail should be null as well, but we just need to check one of them. So we can say if head is equal to null PTR, then that means that the list is empty, right? So basically what the comment is up here, because otherwise it would not be null. So that makes our life easy, because that means that we can just go ahead and insert there. So how do we insert? Well, we basically make head and tail, both of them in this case, point to the new node, which we can then allocate. So new node type T with data inside of it. Okay? However, right now, when we do this, because of the constructor for node, it's setting previous and next to null, which is okay because it's the only thing. So in that case, we are fine. Another scenario would be that the list is not empty. In that case, if there's only one item in the list, that's kind of a nice little scenario, but we will deal with that when we get there. Okay, but now we did one thing, so how can we test that? Well, we could kind of write our print function now and test it that way, or we could test it by hand. But we're gonna actually go ahead and try to do part of the print function now to do that. So how do we traverse a linked list to print it out? Pretty much. Oh, by the way, I guess one way to test our back pointers is actually, let's go ahead and actually have another function called print backwards, and also we can have a recursive print backwards using recursion. Those will be cool to code. So yes, I think we'll add that to the list of things. Just thought about that. Okay, so I'm not gonna put the body to those functions yet. It should compile. Yeah, as long as I don't call the functions. So yeah, okay. So for the print, what I want to do is I am going to do an iterative print, which means that I can basically just loop until I get to the end of the list. So first I'm going to create a pointer that is going to be kind of like my iterator, but I'm going to call that cur, and I'm going to basically set that to point to the head of the list. And what I'm going to do is I'm going to say while cur is not equal to null PTR, so while we're not to the end of the list, then go ahead and print out that node by saying cur print. Okay? And then go to the next pointer, which would be to set cur to be next. Okay? And if you go ahead and do that, then this should take care of basically printing everything. The only thing is that when we call print, it doesn't add any space afterwards. So we may want to add a space between each thing. So like maybe that. Or maybe we want to make it cool, we could do something like that to it. Yeah, that would be cool. Yeah, let's do that. So it'll look like a linked list, like a drawn out linked list. Because of that, then we want to just kind of put the null there. And then maybe print out before as well. So maybe like see out that. Then do the cur. And then the that. We want spaces, yeah. And then at the end of this, we can see out with an asterisk. Okay. Let's see. Missing. Yes, that's what it was. I was wondering why the color scheme was not working. It's because of that. Okay. And then we just need a semicolon somewhere. Okay. So that concludes the print function. I suppose we might want to add an end line to this right here. So maybe end line, and we could head this out by saying like linked list, doubly linked list like that. Sure. Okay. Yeah. All right. So let's go ahead and see if this works with what we currently have so far. To be able to test it, we need to write a little function that inserts something to the linked list. Okay, so let's call that function Dll Tester 1. Okay, and it's going to insert some value that we pass in, maybe 42. Okay, so let's create a header prototype for that. Tester 1 v, and let's actually write that function. So let's just do that down here. So let's go ahead and say template class v void Dll Tester 1 v, and so what we want to do this tester is we are going to make that insert something into our linked list, because we can only insert one thing at the beginning right now, and then we're going to make it print it out to see that it prints out that single item. Okay, and it will conclude our testing. So let's go ahead. Oh, and we need to create a linked list object, so let's go ahead and make one. So first doubly linked list of type v, and call that just DLL for now, and then DLL insert with arrows. It's not a pointer, so it should be that kind of. Yeah, okay. And then let's insert the V in there, which would be a 42, for example. And then let's go ahead and call print on that. Okay, and I think that's pretty much it. That's pretty much all we want to do. So we compile, that's a good sign. If you run it, it says DLL, and there you can see inside that it does indeed print out the 42. So that means that we were able to successfully insert it and then print it out. We do get a to-do that got printed out. That's probably from the Destructor. Yeah, that's from the Destructor. So let's go ahead and actually code the Destructor now, because it's basically the same thing as the print function. We just have to change what's inside of the while loop body. So we can basically just copy paste it. So let's just take that body and put it in here. We might want to, I'm debating if I should make it the destructor be outside. So I think I will do that. Because it is going to be... No, nah. I think it's small enough that it won't need to. So all I really need to do here in the destructor is I can actually use the head. Because I'm not going to ever use it again. So why not? Yeah. So yeah, we'll do it in here. Because it's going to be like 3 lines of code. So what we need to do is say, well, the head is not equal to null. And then we need to delete each node as we go through here. And to delete each node, what we need to do is we need to say, well, here's the way of doing this. If you just say delete head, and then you do head equals head next, then what ends up happening there is you are technically accessing a dangling pointer. And so that's a bad thing to do. So you need to temporarily copy that pointer somewhere and then delete it. So we could go ahead and create a pointer in here and call that temp. And then copy over the value of head. Again, we're kind of reusing the variables here because we don't need head anymore. Otherwise, you would never want to touch head. But yeah, so we're gonna say no temp gets head. Then we go ahead and say delete head, and then we can say head gets temp next. Or no, bad. Do the head first here, like that, and then do the delete temp. Yes. Okay, that avoids you accessing a dangling pointer. The other method would work, however, it's a bad way of doing it. Okay, because you are accessing a dangling pointer because you delete something first and then you're trying to dereference the next. So basically deleting a node and then accessing the next pointer in that node you just deleted, which is bad because it's no longer your memory. So no go. You have to use this concept of a temp pointer. I did talk about this last time. If you're kind of worried about this, just look at the last video as well. Okay, but yeah, so we got a temp pointer, assign it to the current node that we're deleting, and then move over to the next node to delete. But before we actually have to do the deleting by doing this. So the key thing is that we want to do this line of code before we do the delete. Okay. Now let's see if it compiles. It does. Okay, and let's run it again. So this time we don't get a sec fault. Let's see if we get a memory leak. No memory leaks either, and no errors. So perfect. So we have a clean program, nice and clean. You know, feels good. Okay, so and the destructor is only basically 4 lines of code, so not bad. Yeah, we'll leave it in there. Or do we take it out? What do you guys think? Should we leave it in there like this, or should we take it outside of the class? I don't know. It's not big enough that it bothers me, but we could take it out if you guys want to see how that will be done. So I'll leave it up to the chat to decide if we want to leave it in there or if we want to take it out of the class. Let's do it. Let's take it out. All right, let's take it out then. What are the case usages of a doubly linked list? When you're trying to store information and you want to easily print it out backwards without using recursion. So, yes. Again, it's a way of it's an alternative to storing basically data. So yes. Okay. I think I'm gonna need my whole template class thing at the top here, and then doubly linked list. We need to write doubly linked list : but we need to put the T in there : doubly linked list, and there we go. Now we can just dump that in there. Okay, so let's make sure we didn't break this. We broke it. We forgot a semicolon. Okay, now it's not broken anymore. Let's test it with Valgrind. No memory leaks, and then just to see the output easier, we can see that it works. So okay, so we're good so far. We of course have just begun this because we really only have done this insert. So we gotta still do the other inserts. But you know, it's so much easier to test A for memory leaks now and B if this initial insert and the print is working than to just try to code everything at once and then trying to debug like 50 million sec files at once. So you see, it's a much better way of approaching this. So yes, okay. So now let's go ahead and try to insert whenever the list is not empty. And so to do that, we need to find where it is that we need to insert. That's going to be the next step. So basically, as we said there, search through the list to see where we need to insert. Okay. And so what that basically involves is one of two things. You could do this recursively, but we're going to do it iteratively. Okay. Leave it as an exercise to you to make a recursive insert. I do think I might have the solution of a recursive insert in the Canvas notes as well. So, okay. It does look so much cleaner indeed. So let's go ahead and make a cur pointer that's going to help us traverse this linked list. Again, this time we do need one. Before we you know, with the delete, we were using head itself, but you never really want to mess with head. I only use it there because I'm never gonna use it ever again because I'm destroying this class. But I guess one more thing that might be nice to have here to avoid dangling pointers, even though it's in the Destructor, is to set that to null PTR afterwards. Not inside the loop though, outside the loop, like that. Okay, just to make sure that we don't have any dangling pointers. Tail as well. Okay, so we were just here writing this pointer, so no node nor cur, and we're gonna initially set it to point to the head because that's where we start searching from. But you could also do this using the tail, so because there's a doubly linked list, you know. Okay. All right, yeah, that's fine enough. It's just an error for this. So we need to do the same loop here that we were doing before. So cur not equal to basically null PTR. Okay. So while we are not at the end of the list, while we are not at the end of the list, that's basically what this means. Okay. All right. So I think I can hide this for now. So let me go ahead and hide that because we already have that here, and I'd rather you be able to see the output of like Valgrind and things like that in an easier way. Oh, Valgrind's not. Oh, I see. Valgrind is stuck in an infinite memory loop now because of this thing here. But if I comment that out for a second here, oh, recompile first, then you would see that it is memory leaks. Okay. So, all right. So we are going to look through. And so now that we're looping, the way that we get to the next thing, we can go ahead and write that. We can say cur equals cur next. And that's at the bottom of the loop. In fact, it's kind of like our iterator. And then in here, we need to put in code to basically check that specific item and compare it to what we're looking for, which is in data here. Okay, so we can say if it's, how do we know when to stop, where to insert? If you think about it, we want to insert in a location where the next item in the list that we would look at is bigger than what we're inserting, but the item before us is smaller than we're inserting, because that means that we're right in the sweet spot, because we're in the middle between something smaller than us and something bigger than us, right? I guess because it's mirrored, this is technically smaller and bigger. So, you know, if we're looking to insert, we want to hit something right here that is bigger than us, okay? And also, we need to hit something here before that is smaller than us, because that means that's right where we're gonna go, okay? So that's what we're looking for to insert, okay? Like, think about it like you're trying to organize a deck of cards, and you're trying to put in the 5, and you will currently have a 1, a 2, a 6, and an 8. That means that it has to go before the 6, but after the 2, right? So the flag to know that it goes there is because you see a card that's bigger than yours, but also you see a card that's smaller than yours before, okay? So we have those 2 things checked. So what we can do is we can say if data, which is what we're trying to insert, is smaller or greater than, yeah, smaller than. If data is smaller than cur data, which is a pointer, so we need to dereference it. What does that mean? That means that the number we're looking for is smaller than what we are currently looking at. If that is the case, then it means that we have reached the spot where we should insert. Because if we go any further, we're gonna miss our spot to insert. So what it's saying is, you know, if we got 1, 2, 5, 8, 9, and we're trying to insert something, and if we're looking at whatever we're inserting, and we look at this 1, if this 1 is technically smaller, if what we're inserting is smaller than the 1, that means that it has to be something smaller than 1. So it could be 0, -1, which means it has to go before this spot in the list, right? So this number could be basically anything smaller than 1. And so if that is the case, that's the sign to insert, okay? What if what we're inserting is a 4? Well, then that is not going to be true because 4 is not smaller than 1. So then you can move on to the next item to check, which is 2. Is 2, so then you switch this over to 2. Is 4 smaller than 2? No, it's not. So then you keep checking. Eventually, you get to the 5, and you check 4. 4 is smaller than 5, which is a sign to insert. Right? And that's good because that is where 4 would go. It would go right there. So that's what we're going to be using logically to search and find where to insert. So if data is smaller than cur data, which is the node that we're at, then that is the sign to insert. Okay? Otherwise, we keep going. Although, we have to consider a situation where we would insert at the end. If such is the case, if we leave it like this, we're going to hit null and we're going to get out of the loop and then we won't be able to insert. So we want to have another if statement here by saying else if cur next is equal to null. What does that mean? Before I tell you, what do you think this means? If cur next is equal to null PTR, what does that mean about the current node that we're looking at? Where is it in the list exactly? If the element in the list is null PTR, it's at the end. Yes, that's right. It's the tail. It's right at the end of the list. So because of that, we can go ahead and just insert it. Because if we got to this point and this thing was always false, it means that the last item of the list is still too small compared to what we have. So what we have is bigger than that. So we just throw it in at the end. So this is the sign to insert at the end because we are currently at the last node of the list. Of course, don't make a comment .y, you know, KNR, but whatever. All right. So yeah, if that is the case, then we can go ahead and put in the code to insert at the end there. Okay. Whereas in here, it could be the start or the middle still. So over here, what can I use? What do you think I could use to separate whether it's something at the start or at the middle? What could be a good, easy way to check if what we're inserting here is at the start? I could use one of my pointer variables for that purposes. If currently cur, that could work. That could definitely work. That's a good one I wasn't thinking of. So that would definitely work. We can say if cur previous is equal to null PTR, then it must be the first node. So that will definitely 100% work. That's pretty smart. I didn't think about that. Alternatively, the one that I was thinking of, and I'm going to put both in here and I'll comment one out, but I'm going to leave yours because I like yours, is I was thinking of just saying if head is equal to cur, because that means that the head is the same thing as cur right now, which is what we do initially here, then that's also a way of saying this must be the first node. So there you go. With a double linked list, that's a good point. You can definitely do both. As long as you don't break the thing, then yeah, either one of these should work. So they're both the exact same. So I think we'll, what I'll do for now is I'm going to put, because I do want to test both, because like I said, I think both will work, but I like yours. So I'm going to put it down here like this, and then I'm going to comment it out, and then we can just easily flip back and forth later, okay? So we'll do that. I'll use mine first, just because I think mine has less chance of me screwing up personally, because if I screw up the null pointers, then things will go bad. So we'll do that, but we'll definitely test yours out, okay? So in there, okay, if it's the first thing to insert, that's easy to do. Otherwise, by the way, then we will do the insert at the middle, which we still need to do, okay? But let's go ahead and insert at the beginning here. So the way we're going to insert at the beginning is, and again, it's the beginning of an existing list, is the bad thing you could do is just go ahead and say head gets new node and then just code the node in there. That's bad because you've lost the pointer. So what you want to do first is you want to allocate the node. So for that, you know, I could say, just so we don't repeat code, we can go ahead and do that pretty much up here. Before we even go in there, we can create the node first. So let's go ahead and say node t. In fact, we could even do this at the top of this, so that we only create it's easier to keep track of this if we just do it at the top. So the first thing we're gonna do is we're gonna create actually the node, and we're gonna call that new node. Okay, and then just new node t data. Okay, like that. That way here, all we gotta do is basically say new node. Okay. Now here, since we already created a node, we can just go ahead and say new node. Why do you call it head and tail? Because it's the head and tail. It's not me. It's just people decided that a long time ago. It's because the head of the linked list you can think of as the beginning of it. So it's like the head, and then the tail is the back end. So it's the last thing. So yeah, they just picked those names. Some people like top, but that's more of like a stack. So they associate the word top with stack. So yeah, just a name. I don't know. Anyways, so okay, so new node. We need to set the pointers of that. So we need to set next, and we need to set previous of that. And in this specific case here, we also need to update head once we do that to basically say head gets new node, because that's the front of the list. But we don't want to do that one just yet. Also, previous in this case is actually going to be null because it's the first item of the list. So we do need to set head of new node next to point to whatever head is currently pointing at. Then we need to set head back or head previous to point back to new node. So that one's gonna link back. So if we want, so maybe it might help for me to draw. So what each of those lines is gonna do. Okay. So line 61 is going to first, we have our new node that we've created up here. I'm hungry. And we already stored the data of the node, so we don't have to worry about the data. We just have to worry about the pointers. So right now we have prev and next. So line 61 is saying to take the next pointer, which is this right here, and point that to head. And remember, we have an existing linked list. Let me just copy like a piece of this. So we have some sort of existing linked list to this thing, okay? And this is pointing to null, which is very important. And then this is just other items in the list. So what I'm saying is head is already pointing there. So I want to copy the head pointer here so that that also points there. So that's why line 61 is basically saying a new node's next point is gets head, okay? So we point that out. Next, I want to go ahead and make previous here, which is currently pointing to null, to point back to this node, okay? That's line 62. Because I can use the head pointer for that, I can just say head previous and do that. I could have done also, oh, can't see what you're writing. Yeah, good point. I could also do something like new node, next, previous. I could have done this method here as well to be able to access basically the previous pointer of the head, the current head. But it's so much easier to just say head previous, gets new node. So these two lines of code are equivalent, okay? Those two lines of code are equivalent. But as you can see, one of them requires less writing, therefore it's better. Okay, so yes, just again to review, since it might have been off the screen, what I said is your new node next, you want to copy what is currently in head, because that's the same thing that you want this to point to, which is basically to this item here. So that is why line 61 of the code basically says new node next gets head, and then line 62 basically says this here, either of these, but I like the bottom one better. Finally, the last thing we need to do is, because now this is a new head, this node right here, we need to basically flip the head pointer to point to that instead of that. And we can do that in line 63, which basically said head gets new node. And that takes care of inserting at the beginning. Now, there was a couple of questions before. Statistics in discrete math, even nodes and branches also have different concepts. Well, when you're talking about a binary tree, the head is the root of the tree as well. So root could be a useful name as well. But yeah, I'm assuming that in math, they could mean different things. So anyways, that's where those lines of code come from, okay? They look easy, but they're not. There's a lot of thought that comes into those as well. I'll leave it as a comment here that we could have used new node next prev gets new node. That would have worked as well, okay? So that would be like alternative. All right, while we're at it, let's go ahead and do the insert at the end, because that's also relatively easy. All we gotta do there is one more thing we gotta do here. We don't have to do here, but I want to point out the tail does not need to be changed, because the tail is currently pointing to potentially, the first node, but the tail will never be changed if we're inserting at the start. So we don't have to touch the tail at all here. Okay, so just wanted to point that out. Here with the insert at the end, we don't have to touch the head, but we will have to touch the tail. So for inserting at the end, what we can do is we can basically just say that cur next, which is currently pointing to null, is now going to point to the item that we're going to insert. So we can just say cur next gets new node. And then from there, we also want to make sure that the tail gets updated to point also to the new node. And then the last thing is we want the new node previous pointer. The next pointer is already pointing to null, so we don't need to worry about that. But we need to make the new node prev basically point to the last thing, which was cur. Okay, so that will take care of inserting at the end. Does this make sense, or should I draw pictures in the tablet for this? Let me know if you want me to do the pictures of why these lines of code are like this. I just want to make sure you guys are following. It makes sense to me because I've done it 1,000 times, but I mean, it might not. If it doesn't make sense, then now's your chance. Speak now or forever hold your peace. Okay, so you all hold your peace, I guess. If you could, that'd be great. Oh, okay, yeah. So, all right. So in this case, what we're trying to do at the end of the list is if we again kind of pull out from our picture. In this case, we're gonna pull over here because that's the tail end of this. So maybe we'll just pull out these many. So here we got, there's a lot of stuff here potentially, but what we're looking at is at the end, right? Because if you got cur, and cur, was pointing there, but then after that, it's pointing here to the next thing, and then eventually it's going to get to point to the last thing. And then we are checking with a loop. We're saying if, cur next is equal to null PTR, that means that we're at the last item, right? Because if cur is pointing there, it means that cur next is actually this right here, which makes sense because that is actually pointing to null, okay? So how we're gonna insert there is because we know that this is the last thing to insert, and again, if we draw the picture of the node that we're about to insert, which right now is just pointing to null in both directions because we have that in a constructor. As you can see, that's why I love having a constructor in that node class, because we don't have to worry about setting things to null. Everything is set to null by default. It's only setting things not to null that we have to worry about. And it's so easy to run into problems when you don't set something to null, because you kind of just keep going and fall off a cliff essentially. So yeah. Okay, so the 3 lines of code that we have are cur next gets new node, which is coming from the fact that cur is no longer going to be the last thing, because what we want to do is we want to insert the new node is going to go at the end, so it's going to go right there. So what we want to do is we want to update this pointer from being null to point to the new last thing in our list, which is the new node that we just created. That's going to be the last thing. I guess if it makes you feel a little bit better, we'll put it like that, because now it looks more like the one after. Okay, so by doing that, it's the same thing as saying we're going to dump this in here. So maybe let's shrink that out to scale. And we want to make this from null to now point to this node here. Okay? Damn it, I can't draw an arrow. There we go. The way you do that is, again, you just do cur next gets the name of the new node, which this is called new node. So we just say cur next gets new node. So that's where that line is coming from. Okay? And then the next thing we got to do is we need to do one of 2 things first. We need to update the tail, because the tail should always point to the last thing of the list, right? And right now it's pointing to the second to last thing because we added some new thing at the end. So we need to update that, but we'll do that at the end. What I'm more concerned about is updating this previous pointer, which is currently pointing to null, and then basically updating that to now point to the second to last item. And how to achieve that is cur is still pointing to that last item. So if I just go ahead and update new nodes prev, which is the pointer right here, I want to update this to point to the purple node here, which is currently held by cur. And because it's held by cur, then all I have to do is just assign to cur. So that's where that second line is coming from. I could alternatively, this line could also be written by saying new node prev gets tail, because it currently has the old value. So this would be an alternative. So alternative. I'll actually, you're not seeing it here, but I'll switch over to it in a minute. I'm just gonna write it here as a reminder. So alternative new node prev gets tail. Okay, that would be an alternative line of code that we could write. The reason I'm not using that one is because if for some reason our linked list didn't have a tail, I want you to know how to be able to do it. Otherwise, you're like, well, there's no tail, so he didn't teach me how to not do it without a tail, so I'm just gonna give up. So no, don't give up. All right. So that's the second line. Again, these are alternatives, so we're gonna go with this one. And then the final line is we still have the tail pointing to the second to last thing. So we wanted to point to the new last thing in the item, so we want to do that. So that basically just involves saying tail gets new node. Like that. Okay? Alternative line of code would be to say, this one's kind of weird, but it would be basically say cur next. New what? Next. So alternatively we could say something like that. So this would be an alternative. Now, you guys know what I mean by alternative, right? Like I'm saying, it's the same thing in a different way of writing it. You know, depending on how you're feeling that day, I guess. If you want to write that line of code instead. So yeah, that's pretty much all there's to it. That's where those 3 lines of code are coming from. So as I wrote there, I wrote the alternative, and I guess I'll do that here as well. So alternative would be to write cur next. So tail gets cur next. Okay. So now we just need to do the middle, the dreaded middle. That's the one that's the hardest, because that involves moving more pointers around. 4 pointers essentially that we have to deal with. We have to deal with the nodes previous and next. We also have to deal with the node before us next and the node after us previous. So that's the harder one. But before we go there, let's go ahead and test the other ones to make sure they're working. There is one more thing that we need to worry about in this code. The way that this is written right now, if we do one of the insertions, we're still looping around. And if we do, that's bad, because we could keep trying to insert something over and over again forever. So what we need to do is we need to be able to break out of this once we've done an insert. One way to do that, one getaway way of doing that, is to put a break after each of these lines. So like break here and then everywhere else. However, I'm going to do it with a sort of less ghetto version of that, which is I'm going to put the else here like that. And then I am going to say that, how do I want to do this in a not so bad way? I think maybe I'll leave it like this, but I'll put 2 breaks. I'll put 1 break here, and I'll put another break here. Actually, not even a break, a return. Like that. Okay? Yeah. That should avoid accidentally trying to insert twice, okay? Because once we insert something, we're done with the function. So don't keep looping around and potentially doing bad things you shouldn't. Once you've done the insert, just get out of there. You know? Get out of the functions. So we could also use a Boolean flag and then check the Boolean flag here. You know, I guess that's a more elegant way of doing it. So yeah, I guess we'll do the more elegant way. Boolean done. Set it to false initially. So we'll say while current is equal to null and not done, then we can go ahead and say done gets true here. And then here we can say done gets true. Okay? I guess that's a more elegant way of doing it. I still think the return is better, but sure. Okay, I really honestly think that we should test at this point before we do the middle. So let's go ahead and write another test function for this. So we're going to call that Dll Tester 2. Dll Tester 2 is going to not take, no, we are going to take parameters. We're going to take 3 things of the same variable type. So we'll call it v1, v2, and v3. Basically just to insert a couple of things, you know, to make sure that they're inserting. And they're in increasing order. So actually, you know, we'll make this one just be with integers because we already tested whether the template part works with this. So that will not take any parameters. Yeah. We still need the template, but we won't take parameters. Like that. Okay? And so in this scenario here, where's our main? We'll say DLL. We're here. Otherwise it's going to complain at us. Dll Tester 2. And so Dll Tester 2, the job of this function is going to be test the insert in the beginning and in the end. Not just if it's empty, but just beginning and end, okay? We already checked whether the empty one will work. Well, I guess this will also test that inadvertently. However, this one's only going to test it for integers because it makes life easy. So in this case, we are going to... So I guess if we have that, yeah, we don't really need that. Yeah. So let's not put it in there. Okay, so this one's just going to make integers and it's going to insert into there. Let's just say it inserts a 5. And that one's going to be the same as above. So then what we want to test is we want to test to see if something smaller will insert at the beginning. And then we test it one more time. And then also we want to test stuff at the end. So we want to insert something at the end. So maybe like a 7. And then an 8. Notice that we're inserting either all the way at the beginning or all the way at the end. Not at the middle because we haven't coded that yet. So yeah, we expect to see here a 3, 4, 5, 7, 8. Okay? We shall see if it works though. Okay, we have an infinite loop, so I'm glad that we tested it now because we have a problem. Let's see what the problem is. Done gets true, well, and not done. If done is true, then this is false, so we should kick it out. Douglas Adams is please. Who's Douglas Adams? If head is equal to null. Well, here let's use GDB to find out where that is looping forever. So GDB. So here, let me recompile again with the G flag, and then GDB a.out, and then let's set up a breakpoint in the insert function. So actually no, let's just run it and then we can pause it. How do we pause GDB execution though? I don't know how to pause it actually. Okay, well, Control C pause it. There we go. So let's see where we're at. Backtrace. Double linked list print. Oh, it's the print function that's broken. Well, that's probably not true. That probably just means that we broke something in here. But the print function was a side effect of that. But just to confirm that, let's comment out the print function and see what happens in that case. Oh, it does make sense that it's broken, because you see it's printing forever. So that actually does make sense, that is indeed broken. Although it's broken even for the 42. I see. We probably never messed. Okay. I think I might know what's up with this. So I think here, if head is equal to null, head tail gets new node. Yeah, so the problem was here. Okay, so the problem is right over the hitch. The problem is as follows. We insert the node 42, but then we try to insert it again here, and so it inserts it at the end of that. So we have a linked list with with an infinite amount of 42s in it potentially, which is why it's printing forever there. And so what we need to do to fix this is we need to return at this point. But again, because we're using this Boolean thing, let's just move the Boolean even higher in the code. And then just say here, dumb gets true. And then that way, it will never go into this while loop, which should take care of our problem. Okay? At least that problem. I don't know if it's going to have other problems, but... Yay! Okay, we fixed that problem. So now we can go ahead and call the print functions here and see if this one worked as well. So there you go. We had our bug of the day. I knew that we wouldn't get to this without a bug. It's just too much code to be doing on the fly here on live. However, surprisingly enough, the other part, which is the more complicated part, actually is working just fine. As you can see, we were able to insert in ascending order like that, also known as non-descending order. So that is working fine, actually. That part is working fine. So that was a relatively painless fix. As you can see, I mean, it was obvious now in retrospect that I was seeing a bunch of 42s. It would make sense that it was because we're inserting forever, but it didn't make sense then. But that is why GDB is a homie, because GDB told me that there was something with the print, which kind of was like signing to me that something was wrong with the insert. So yeah. All right. So now we got to do the middle insert. That's a tricky one, okay? If we go back to the tablet here, I think I showed you how to do that up here. Yeah, right here. So that's inserting at the middle, which means that we have to not only first find the location, which we already did, because that's in the else clause. It means that we are there. But now we need to deal with the pointer before and the pointer after. And the thing is that once we get here, where's my pen? You know, we are currently here. Let me copy actually this so I don't modify this version of this. Come on. Okay, there we go. Copy. Pasta. All right. So this is what we got right now, except for the bold lines. Those are not there. And we are trying to insert something in. Well, let's say that. Yeah. Let me jank this out. Oh, I broke it. Here, like that. And right now, this is the scenario that we have. This is called new node, and it's pointing to new node. I guess to not make you think that it's pointing to a specific part of the node, let me just kind of put it a little bit further away. Okay? And previous and next are pointing to null. And then down here, we've got that. Okay, and the reason I'm leaving that space is because it's going to make it easier to show you. Okay, but they're just connected. connected. So we already took care of actually locating the spot that we have to insert at. That's the good news, okay? We already did that, actually. So, and it turns out that we have a pointer called cur that is pointing to the item after what we need to insert, okay? So that's pointing there. So what we need to do is we have this information and that's all we need. Let's do this in steps. The first step that we're gonna do, and for that actually let me get rid of this purple color from this. Yeah, is we are going to assign this next pointer to point to cur, which is currently being held, well, to cur, which is the next node, okay? So we want, in essence, to make this pointer go from null to point there, okay? That's step one that we want to do. How do we achieve that? Quite easily. That's not the hard part. New node next is going to get cur, okay? Bam, done. 1 out of 4 done, 1 out of 4. Quarter of the grade done, okay? Next, we have an option of things we want to do, but the one that we don't want to mess with yet is this one. We don't want to mess with this line here because that's the only way that we have access to the item before us. So we don't want to mess with that one. That's the last thing that we want to change probably. So actually, let's go ahead and set new node's previous value. So new node prev. We want that to point here. So how are we going to get that value? Well, we got cur over here, right? We got cur that we can use for that. So how can we use it for that? Well, cur prev is pointing right now to that previous node. That's why I said we don't want to delete it yet, because we're just about to use it right now. So we can do that by saying cur prev. And cur prev will hook us up with getting to that last node. So just to avoid confusion with the colors, let's get rid of that color like that, okay? So there we go. And then this is red, and then this is like some sort of orange, I guess, okay? So like that. So doing that line of code will guarantee that we have now ability to sort of partially link this thing using the new node, okay? So now what we gotta do is we got to point cur prev to point to new node, and we also need to have this guy point there. So that's the tricky one. So let's go ahead and do that one next, okay? So let's go ahead and make the previous nodes here point that way, okay? So we want to basically cut this link here and instead make it this link here, okay? So what we're gonna do is that is currently held in cur prev, okay? Which is also being held in new node prev. So what we're gonna do is we're gonna say cur prev, or alternatively new node prev. These two are the same line of code that we're about to do. This will, either of this takes us to this node right here, okay? So, and more specifically to the brown part of the new node. So this one right here, okay? That one right there. Okay, so that is taking us there. So again, those two lines of code are interchangeable, okay? So what we want to do is we want that to point to new node. That's the pink link. Okay, again, you don't need both of these lines. They're alternate. So like, just pick one of the two. Which one do I like to pick personally? I don't know. I really don't know. I think I'd go with the cur one, just because I don't like this whole idea of new node prev gets new node. That sounds weird and might be confusing to somebody. So even the dog is like, no, bad thing. So yeah. So we'll go with that one, okay? And then finally, we need to have this pointer here from this, which is currently being held in cur. However, this is a bit of an issue here. Yeah. So here's the thing: depending on what you've done here, you got to be very, very careful about this, because hold on a second. Maybe these are not interchangeable. Hold on. Cur prev. Yeah. So actually, this one. Apologies. This needs a double prev here to be able to be the same thing as the one we needed. Oh no! It doesn't. It doesn't. So it's good like that. But here's the thing though. Hold on, I'm thinking for a second here. No. Okay, so this one's the one that's wrong. This one. Yeah, just forget about that line of code for a second here. I was showing you to do this, to do this link here. The green link, okay? The green link is actually already done. Yes, it's the pink link. Yeah. Okay, so the pink link works as it is now because we haven't touched cur yet. Okay, and so that works fine. However, new node prev. Oh yeah, so never mind. I'm freaking out. It was fine. We were fine. So sorry. I freaked out for a second. Isn't cur prev what we just set? Should be the first, not be cur prev next. I'm thinking for a second here. I'm trying to see. I think we just did everything, and so it's more of like cur prev gets new node, and then new node prev gets. Okay, so I think the issue here is this. New node previous is not supposed to get new node. Yeah, okay, so the problem is this one. And this line of code needs to go before this line of code. Or we can just get rid of it entirely. Trying to think for a second. Oh, this is tricky. Yeah, let's backtrack for a second because I lost myself here and I feel like I'm gonna make a mistake. So let's just backtrack to what we had, okay? And just go from there. So right now what we have is we have that and that, okay? So we have these still pointing back and forth, okay? So we just set that. So now we gotta set those two, okay? So let's start out by setting out this one here. I know what I forgot. The next part. I forgot the next part. That's what it was. Okay. So what we want to set up is we want to set up the pink link that we had. So we want to do this. Okay. So that is what we want to do. That is actually held in cur prev next. That's where that's held. Okay. That's what we want to set to new node. So I forgot the next part of that. Okay. That is how we set this guy. So the way we're doing this is we're basically saying cur prev is this, and then that gets us to this node, and then we want to access this value in the node, which is how we get to that. Okay? So that is how we set that. That's how we basically change this link here, okay? But we haven't deleted that link just yet. We're using it to our advantage because the one we're actually modifying is the bottom line here, okay? An alternative way of doing this line of code, which is what I was trying to do earlier, was that you could just use the word new node prev next would get you that, okay? So either of these would work. New node prev next means go to new node here, go to the prev in there, which takes us here, and then go to the next one and change that, okay? So either of those, you need the word next along with that, okay? So you were right in that, okay? Cur prev next. All right, so yes, these are the alternatives. And don't worry, we'll end at the insert and then we'll pick up tomorrow for the delete. So we're almost done here. Okay, so from there, the last thing we need to do is we need to go ahead and make this point here. So that is currently held in cur prev, which now we just want to point to new node. Okay, and that's just going to basically severe this link and replace it with this link here. Okay. Alternative way of doing that, which would be weird, would be to do new node next prev gets new node. Okay, so yes, let's go ahead and just write that in the code, and then we shall call it a day. Okay. So I'm just copying the exact lines of code like this. Okay. So we got new node next gets cur, and then we got new node previous gets cur previous. So cur is currently pointing to the node after where we want to insert. So because of that, we are putting the next one to be cur, and then the previous to get the previous one of the one that we are after. And then come in the extra 2 pointers, which we can use either of the 2 lines that we have. So one of them is cur prev next gets new node. So that's pointing the node before us to point to the new node that we're making. An alternative way of writing this would be to say new node prev gets next, like that. And the other line of code that we need is going to be to put the link from the node after us to point back to us with the previous pointer of that node. So for that, we can just say cur prev gets new node, or alternatively, we could say new node next prev comes to new node. Okay, and that's it. Those are the 4 lines that we need. Yes, so I can try and go over this next time because I don't have time right now, because I'd rather just test it first, and then we can go over it and pick up from there next time. Okay, so let's quickly test it. Let's just modify our Dll Tester 2 to also check that. And the way we can do that is somewhere in the middle here, we can go ahead and insert. So we got 3, 4, 5 here at the end of this. Let's go ahead and actually, before we do anything else, let's just run it to make sure it's still working. Oh, snap. What did I do? Oh, I tried to change the 2 to 3, so leave it at 2. So it's still working fine. So now we're just gonna try to insert something in the middle. So let's go ahead and insert a 6, because that's right in the middle, right? Yeah, a 6. And if we do that, we can see that it inserted 6 successfully. And more importantly, let's check with Valgrind. We don't have any memory leaks or errors right now, so everything is fine. So it works successfully. I could show you, maybe make this a 10, and then we can also insert a 9 in here, because right now if I leave it like this, we can see that
we have a gap. Everything is working, but now we have a gap, but we can also insert like an 8 and a 9 just to triple check that it's still working. So we can insert an 8 here, and then maybe a 9. Here, let's insert first a 9 and then the 8. So 3, 4, 5, 6, 7, 8, 9, 10. So there you go. It's working just fine. So we have successfully completed the insert function. It'll insert into a sorted list. So it'll automatically sort it. And yeah, as you can see, the full line of code for that is right there. I can't fit the full function in. It's almost in there as well. But there you go. So what we will do is we shall pick up from this tomorrow. And we will create the delete function, which is not as bad, but we also have to consider those 4 scenarios that we did for the insert, except sort of reverse. And then once we finish the delete, then I think we will go ahead and do a print backwards using the previous pointer, which will be super easy to do. And then we will do recursive one-to-one recursion as well. And then that will probably take us about half the class, and maybe the second half we'll do quickly stacks and queues. But that's the plan for tomorrow. All right. So, yes, I have a question. The delete function in the skeleton code for assignment 12, is that supposed to be like the destructor? If you're talking about the, what's the name of the function? It's called like wake them up or something, or the dream is collapsing. That does work as the destructor, okay? I think it's called wake up. You can correct me if I'm wrong. But yes, that does serve as a destructor, because when you're waking up, everything gets basically destroyed in the dreams. So yes, cool. That's pretty much the class. So as you can see, no, it's for the linked list assignment, not Inception. I don't know in that one. I don't remember for that. But the delete function typically will delete the individual nodes, but you might still need to add another destructor. I'm not sure. So just add whatever you need to avoid memory leaks. You are free to do whatever you want in that program to avoid memory leaks. It's only in the Inception one where you shouldn't mess with main, because that doesn't require anything. So yes, okay, cool. Yeah, that's pretty much the class. So, oh, I didn't mean to do that. So okay, well. Until then, make sure you guys work on your assignments, and we shall pick up from Doubly linked list next class. So yes, I will. I am starving, so I shall go and eat. So see you guys tomorrow for almost the second to last class, right? Or actually tomorrow, no, tomorrow is the last class. So one left to go, and then the midterm, and then or the final, and then we're done. So see you guys. Have a good night. Peace.